the Andromeda Galaxy stands out like a shining jewel. Imagine this. If we could travel at the speed of light, it would take us nearly 2.5 million years to reach it. It is the closest galaxy to our Milky Way and contains about 100 billion stars. These stars are not just bright points in the sky, but places that may hold Earth-like planets. According to scientists, Andromeda could be an ideal place for life. Is someone out there looking toward us from a planet somewhere in this galaxy? How could we possibly make this journey? Current technologies, such as spacecraft, can reach speeds of about 58,000 kilometers per hour. However, researchers are exploring bold ideas like traveling through space using nuclear engines or even warp technology. Let's explore these wonders together right now. Every journey away from the solar system must begin with facing our own home, Earth. It is not just a blue planet orbiting the sun, but the place that holds all of humanity's history, memories, joys, pains, and every unanswered question. When viewed from the ground, Earth seems endlessly vast. Rolling oceans, sprawling continents, cities glowing bright at night. But when seen from the outside, everything shrinks into a fragile drop of light in a boundless sea of darkness. When we leave Earth's surface and rise into low orbit, from about 100 to roughly 2,000 kilometers above the ground, the familiar world instantly changes. But what overwhelms humans is not the harsh environment. It is the view of Earth from above. This is the place where the overview effect, the cosmic awakening, becomes a real psychological phenomenon. Most astronauts describe it as a direct strike to their awareness. Anyone who sees Earth from orbit can never return to the way they once thought. From low orbit, we also grasp the true scale of the universe through one shocking detail. All the planets in the solar system can fit within the distance between Earth and the Moon. This shows that the solar system A structure we consider enormous is actually unbelievably small when placed in a larger context. Farther out, the observational tools humanity has developed, such as the James Webb Space Telescope and Gaia, are gradually dismantling the limits of what we can perceive. In 2024, both detected water molecules in interstellar environments near Earth, a kind of signal showing that the conditions necessary for life are far from rare. If water, the basic molecule of biology, exists in molecular clouds just a few hundred light years away, then life may have already formed or may be forming in places we never imagined. From low orbit, we see that life exists only within an astonishingly thin layer, from the deepest ocean trenches to the peak of Mount Everest. All life occupies a narrow band, less than 20 kilometers, within the total height of Earth's atmosphere and crust. But it is at this starting point, where we look back at Earth in absolute silence, that we understand a fundamental truth. To step into the universe, humanity must learn to leave behind everything familiar. But leaving low orbit is only the opening chapter. To truly reach Andromeda, we must cross a far greater boundary, a boundary separating humanity from the rest of the galaxy. And that boundary begins the moment we attempt to leave the solar system. To leave the solar system, we do not simply cross a physical space. We cross a psychological boundary that humanity has never truly confronted. To escape Earth's gravity, a spacecraft must reach a speed of 11.2 kilometers per second. This seemingly abstract number carries a very concrete meaning. It is the speed at which every sense of slow, fast, far, or near becomes meaningless. To escape the pull of the very star that has sustained us, we must reach 42 kilometers per second, the sun's escape velocity. This is an immense energy barrier that no primitive civilization could ever surpass. The fact that humanity achieved this with small probes like Voyager and New Horizons is proof that intellect can compensate for the frailty of the human body. But the moment we surpass the sun's escape velocity, no matter how far we go, we still remain inside the heliosphere, a gigantic magnetic bubble about 200 astronomical units AU across, created by the flow of the solar wind. Inside this bubble, the sun still protects us from 99% of the high-energy cosmic radiation produced by supernovae in the Milky Way. But this structure is not infinite. It has a boundary, the heliopause, where the pressure of the solar wind weakens completely and gives way to the interstellar medium. One human spacecraft has reached that edge, Voyager 1, launched in 1977. After more than 45 years, it finally exited the heliosphere in 2012. But the most striking part is not the time, it is the distance it has achieved. Voyager 1 is now about 24 billion kilometers from Earth, which is only 0.00024% of the journey to Andromeda. Voyager 1 does more than send back positional data. It sends back a truth that earlier models never accurately described. The interstellar medium is not an empty vacuum. Data from 2024 shows that Voyager is traveling through a denser than expected plasma region with electron densities around 0.04 cubic centimeters, nearly 10 times higher than predictions made for decades. This proves that the space between stars is a constantly shifting network of plasma waves, magnetic fields, and streams of high-energy particles generated by nearby stars. What science warns is that interstellar dust is not just a risk, it is one of the fundamental obstacles to the dream of interstellar travel. According to physical simulations, Even a single collision with silicate dust at 0.1 C can generate a force equivalent to a grenade explosion against a spacecraft's hull. But humanity never stops at the first barrier. The future technologies we are developing show that the desire to leave the solar system has never faded. Through Starshot is a proposal to use ground-based lasers to push lightweight probes using photon pressure to 20% the speed of light. Fusion drive nuclear fusion engines, preeminent fuel efficiencies tens of times higher than chemical engines. Antimatter propulsion is the most energy-optimal technology ever conceived, where each gram of matter and antimatter can release energy equivalent to a nuclear bomb. There is even the concept of Alcubierre's warp bubble, though unconfirmed as feasible, which opens the possibility of bending space-time to travel faster than light without violating relativity. But leaving the solar system is not only a matter of technology, it is a matter of time. The distances to the stars are challenges not only of physics, but of civilizational endurance. Models show that even at 10% the speed of light, a spacecraft would need about 40 years to reach Proxima Centauri, the closest star. But if the target is Andromeda, then the scale enters an entirely different realm. For Andromeda, 0.1 C would require 25 million years, 0.5 C would require 5 million years, and even at 0.999 C, where time dilation allows the crew to experience only a few thousand years, the external universe would still continue for millions. From the sun's outer boundary, when its light becomes just a faint golden thread, crossing beyond its frontier only opens a new region for humanity, an endless desert where stars are nothing but distant oases. Crossing beyond the heliopause, the boundary where the solar wind fades and the interstellar medium begins, our spacecraft enters a region so vast that every human word becomes small. Interstellar space is not a hallway connecting stars. It is an endless desert where light stretches until it loses its color, where every concept of distance becomes surreal. And in this silence, we finally feel the true scale of the universe, a frozen, dark ocean stretching tens of trillions of kilometers between each star. In this place, the nearest star, Proxima Centauri, 4.25 light-years away, is no longer just a measurement. Becomes a challenge to imagination. 1 light year equals nearly 9.46 trillion kilometers, making the distance to the nearest star feel like trying to walk across the entire history of Earth, till the age of dinosaurs to the modern era. In the interstellar medium, matter density falls to about 0.5 hydrogen atoms per cubic centimeter. That is so sparse that if you took a room-sized volume of space, you might find only a few lonely atoms. But the universe's paradox is this: Scarcity makes this place dangerous. At high velocities, every tiny dust particle transforms into a bullet with immense kinetic energy. At 10% the speed of light, even a microscopic grain of dust can create an impact equivalent to a gunshot, punching through a spacecraft's hull. Interstellar space is also where temperature reaches nature's lowest floor, around 2.7 Kelvin, just a touch above absolute zero. Air does not exist, sound does not travel, and every familiar physical sensation disappears. Stars do not twinkle, light does not scatter. No dust clouds, no gas streams, no motion close enough to sense. Only darkness, stretching without end. But this desert is not entirely quiet. It is filled with high-energy cosmic radiation, protons, electrons, and heavy nuclei accelerated by supernova explosions, moving at nearly the speed of light. These particles can pierce spacecraft armor, destroy cells, mutate DNA, and damage electronics. That is why leaving the solar system is not just leaving behind a familiar source of light, but also stepping away from the natural shield the sun provides, the heliosphere, the magnetic barrier that protects us from most cosmic rays. In the interstellar region, that protection is gone. A spacecraft must create its own shield using artificial magnetic fields, ultra-thick protective materials, or plasma-deflecting systems. But even these technologies exist only in theory or early laboratory testing. Can a civilization built on biology truly survive in a realm shaped for physical processes rather than living organisms? Interstellar distances pose another challenge: time. If a spacecraft reaches 0.1 C, reaching Andromeda requires 25 million years, 5 times longer than the time since humans diverged from apes. At 0.5 C, the journey still lasts 5 million years. And if we approach 0.999 C, where time dilation becomes profound, the crew may experience only a few thousand years, while millions pass outside. And this creates an existential paradox. Travelers and arrivals may not only belong to different generations, but different species. In this vast emptiness, the Milky Way begins to shrink. Interstellar space forces us to face another truth. A spacecraft can shield against radiation, dust, and impacts. But no technology is strong enough to shield against loneliness that lasts across generations, unless we learn to find meaning in the journey itself. And when we cross tens of thousands of astronomical units, when the sun becomes just one of hundreds of billions of faint stars, when Earth's memory fades into an ancestral echo, that is when we approach the next boundary, the edge of our own galaxy. For the journey to Andromeda does not pass only through space. It passes through the layers of human perception, and the next step will transform how we see the Milky Way. From the inside, we see the Milky Way only as a faint glowing band. But from the outside, it is a massive whirl with two major spiral arms, Perseus and Scutum Centaurus, and smaller ones like the Orion arm, where the solar system resides. Gaia's data has measured the motion of over 1 billion stars, allowing us to reconstruct the galaxy's precise structure, a thin spiral disk slightly warped at the edges, with a peanut-shaped central bulge, surrounded by a hot gaseous halo at 1-2 million Kelvin, stretching more than 200 light-years across. To see the Milky Way from afar is to look at the age of our own existence. The galaxy formed 13.6 billion years ago, less than 200 million years after the Big Bang, one of the oldest surviving galaxies. It has devoured dozens of smaller galaxies throughout its history, leaving behind tidal streams that stretch tens of thousands of light years. At this distance, a discovery in 2024 makes the Milky Way even stranger. The galactic wind, the intergalactic outflows blowing from our galaxy's core. Chandra and Air Rosetta detected streams of hot, highly ionized gas shooting outward at speeds up to 1,000 kilometers per second. They are not simply escaping gas flows, they interact with nearby galaxies in the local group, potentially influencing how satellite galaxies form stars. The most striking realization is not that the Milky Way becomes smaller, but that it was never large. At tens of thousands of light years away, the Milky Way no longer fills the view. It occupies only a small portion of the sky, much like how the Sun appears once we leave low orbit. Beautiful, but no longer commanding. The galaxy that nurtured every form of life we know becomes just one among hundreds of billions. And as our perspective widens, smallness stops being frightening. It becomes a liberating truth. We were never the center of anything. From here, we begin to see the interaction between the Milky Way and Andromeda. Studies from Hubble and Gaia show that the Milky Way is moving toward Andromeda at 110 kilometers per second. Seen from afar, the two galaxies are no longer separate points of light. They are pulling on each other in a gravitational dance that began billions of years ago. This is not a distant future right now. Our entire galaxy is already moving along a collision course. As the light of the Milky Way fades behind us and the ship travels far enough that our home galaxy becomes only a fragile speck, the first thing that appears ahead is not a clearly defined spiral galaxy, but a faint streak like a breath fogging the glass of the universe. At a distance of millions of light years, Andromeda begins as a strip so thin it could easily be mistaken for a dust cloud or an unfamiliar nebula. This is no longer just a point of light. This is the galaxy 2.5 million light years away, rushing toward the Milky Way at 110 kilometers per second. And it is the destination of a journey humanity never dared to dream of before the 21st century. At a close enough distance for details to emerge, we begin to see spiral arms extending hundreds of thousands of light years. But Andromeda's uniqueness is not just its size. Observations from Hubble, Gaia, and JWST reveal that Andromeda is wrapped in countless tidal streams. Ribbons of stars torn apart and scattered across the galaxy's halo. These are the remnants of dwarf galaxies Andromeda has consumed over billions of years. Each stream a scar from a galactic merger whose fate was sealed by gravity. As we approach further, we begin to sense its immense gravitational field stretching across millions of light years. Physically, even the Milky Way's orbit is being bent by Andromeda. According to 2023 NASA data, the unexpectedly large mass of the Large Magellanic Cloud, LMC, has shifted the Milky Way's center of mass and altered the collision trajectory between the two galaxies. This shows that we are approaching a galaxy not only massive, but powerful enough to reshape the motion of an entire system of satellite galaxies. When the distance shrinks below 1 million light years, Andromeda's light expands until it occupies nearly the entire field of view. In the outer halo, temperatures of ionized gas have been measured at 1 to million Kelvin, forming a vast envelope surrounding the galaxy. JWST and Chandra have confirmed that this halo is significantly larger than the Milky Way's, containing matter that will fuel star formation in Andromeda's future. Star-forming regions where hydrogen glows in bright red, where young stars ignite into vibrant clusters seconds for thousands of light years. Every second, a new star is born in Andromeda, a natural cycle of cosmic renewal. Looking closely, we see brilliant blue star clusters, much hotter and more massive than the Sun, only tens of millions of years old. These are OB associations, where massive stars form and explode over extremely short timescales. In the central region, a peculiar feature of Andromeda appears. Instead of a single central bulge like the Milky Way, Andromeda has two optical nuclei, one resembling a classical bulge and one shaped by a tilted stellar disk. This is what makes Andromeda unique. And then, at the heart of Andromeda, hidden behind layers of dense starlight, is a supermassive black hole weighing 200 million suns, a place where physics bends, where time stretches so dramatically that a single minute outside could be years within. The imagined journey to the Andromeda Galaxy has revealed a fundamental truth. We are small beings within a cosmic structure far too vast, where every star system, including our own Milky Way, exists in a state of constant motion and perpetual transformation. The distance of 2.5 million light years is no longer an absolute physical number. but a measure of the limits of our current technology and the boundless capacity of human thought. It is this ability to simulate and the desire to surpass such boundaries that affirms human intelligence, the very force that has carried us from a small planet to mapping an entire intergalactic journey. Science does not merely draw the map of the universe, it opens the map of our own understanding. In the end, the voyage to Andromeda is not about searching for a new destination, but about redefining our place within everything. The upcoming collision between the Milky Way and Andromeda is not just an astronomical forecast, it is a reminder that we are part of a grand cosmic destiny. Earth may be small, but our desire to explore, to reach for life and truth beyond, is infinite and without any boundary.
Columbia, you are go for orbital drift. Maintain trajectory over the Atlantic.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.